Well, thank you for the intro. Tough start to the morning here. I've been in statistics and Gaussian regression talks all morning, so my head's getting a little full. But while everybody's sitting down, I'll just point everybody out. This is contact info for me in case you want to get a hold of me. And I did push the slides up on SlideShare. So my name's Mike Pittaro. I'm going to start off this talk, since we're talking about hardware, slightly different for me. I'm usually giving talks about code, Python, and things like that, but I'm currently working as a big data architect at Dell. So there was some interest about hardware for high performance analytics, and I figured I'm going to try and squeeze this into a short session. You know, we got about 40 minutes. I can't cover everything. So what I'm hoping is that I can go deep enough to help you understand some of the trade-offs involved when you're building mainly clusters, but also just picking out workstations. Get you to the point where you're intelligent enough to know which questions to ask and which ones don't matter. And frankly, to learn from what other people are doing. There's kind of a body of knowledge here around clusters and high-performance computing that doesn't always make it out to developers, particularly in the data science space. So my approach, I kind of struggled with this. I wasn't sure how to do this talk because I realized I'm dealing a lot more with programmers, and usually I'm talking to people that live and breathe this stuff and know it better than I do in some cases. So my approach was, let's spend a little time talking about why we want to look at the hardware. Then I'm going to start with an overview of a production cluster design, something we're selling now as a product, and then I'm going to go backwards and take it apart and look at the individual components in it and explain some of the trade-offs that were involved in the design. My day job, I'm a principal architect for big data solutions. I'm actually in engineering, so I'm not a field consultant with customers. I think architect is becoming like a systems analyst these days. Everybody's an architect. But my job is to design clusters and document them in the form of what we call reference architectures or blueprints that our customers can then use as the basis to implement something. My background is data warehousing, data integration, and supercomputing when I was much, much younger. So I used to deal with C and Fortran. These days, I'm pretty much a Python guy. I really haven't written Fortran in about 15 or 20 years, and I dabble in C, but I wouldn't call myself a C programmer. So as I get into this, one of the things I wanted to ask as I'm going into the talk, I'm going to talk a little about why I consider the hardware, but one of the things I want to ask is, for the people in the room here, I'm making some sort of an assumption that you understand Hadoop or Spark or parallel processing. Is everybody okay with that assumption for now? The other thing I was going to say about Q&A, I'll try and leave time at the end for Q&A. I think we'll have enough time. But if I say something that just knocks you out of your chair and you have no idea what I said, you know, interrupt me, ask a question, ask me to clarify something. Don't sit there being confused, because there's a lot of acronyms here. So from the top down, I mean, one of the questions is, why do we really want to ask about the hardware? Why do we want to think about it? One reason is the choice of hardware actually has some pretty big impacts, both on your wallet and on the performance of your programs. Personally, I've spent my career dealing with both hardware and software. I think understanding something about the hardware helps you write software. There are people here like Andy that really understand the low-level details of the processors and optimize things, but in general, it helps to understand what's on iron you're running on. Another issue, it comes up quite often, hosting things in the cloud, whether it's just using servers at Rackspace or some ISP, or using the Amazon cloud, or one of the other ones. There are a lot of people that either can't put their stuff on those machines or just are not willing to it. You know, there are some people that feel strongly they're in the retail sales business and they don't want to run their infrastructure on Amazon because Amazon competes with them. And they feel strongly about that. Also, you'll hear horror stories about operating costs going too high. It depends on what you're doing, but you can run up a pretty big bill if you're not paying attention. And there are guys that actually use algorithms to optimize their machine usage on Amazon. It's kind of like a little niche market. And you know, sometimes you just need the performance. There are trade-offs when the machines are remote and you're always running over a remote network. Sometimes you just need local performance. Another killer reason becomes more important when you're in the big data space. Data's heavy, so you don't want to move a lot of data around. A local cluster usually has persistent data, so you fire up a job, your data's there. When you're done, it's still there. You don't have to worry about sucking it all out and shutting down a cluster. And when the data gets big enough, it's expensive. So that's really why we're talking about hardware. There are a lot of other reasons, but here's the problem with hardware, and as I said, I spent a lot of time working in both of these fields. The problem with any sort of big data hardware is there's a lot of options. Servers, processors, GPUs, you're dealing with drives, you're dealing with networking, you're dealing with jargon and acronyms that have been developed over the course of 20 years, and you're dealing with a lot of misleading information. You'll see recommendations on Hadoop nodes on the internet, Google Hadoop hardware recommendations, you'll see something 6 years out of date. And a lot of these blog posts aren't dated, which is a personal nit of mine. You know, blog posts should be dated so that we can put them in historical context. But anyhow, there's a lot of confusion, there's a lot of pieces. Most of our customers are interested in something that is going to work. They want results. They understand the technology, but they're interested in performance. They're concerned with reliability. They want something that's predictable. They're concerned with cost, so cost management comes into play. But in general, they're looking for something that's proven and tested. So rather than a set of tools, they're often asking us for a finished product. The work that I do is between these two primarily. I work on things we call a reference architecture. It's effectively a blueprint. So when a customer is looking for a Hadoop cluster or Spark cluster, there are some documents available that describe how to go about and build one. And it's tested configurations. We have products where we actually test that configuration in a lab, but it's tested. We have an idea of the software. We can make recommendations at a low level on BIOS settings and so on. But it's a blueprint, so it's not a fixed configuration. Normally somebody will pick that up and then we'll start tweaking it. The secret to these architectures, I know I'm giving away the dirty secret of all the hardware guys, but the secret to any of these architectures, it's not that one's better or worse. It's all about balance. You're dealing with a price constraint, you have a performance constraint, you have a particular application you're running, and you're trying to balance that all and come up with something that catches all those constraints. But behind the scenes, you're always worrying about fault zones. Because when you add this many machines, you will have a problem where you're going to have failures and you have to account for them. The way I was going to handle this is to go backwards. I'm probably going to go over here and point because for this picture I just want to point some things out, but other than I'll be back to the computer. I just finished up a project we call the Dell in-memory appliance for Cloudera Enterprise. It's a new offering for us in that it's a packaged Hadoop cluster that's been optimized for large memory footprints. And I'm just going to point out the pieces here in the rack, and then we're going to go back and kind of drill into the individual choices. This particular system, it's a Hadoop cluster. You can get up to 4 racks. Most customers will buy, in the beginning, just 1 rack or 2 racks, and then they scale out. These machines down here at the bottom of those 3 racks are the data nodes. So these are the ones that are doing most of the Hadoop processing. The first rack over here has 4 nodes at the top that act as infrastructure for Hadoop. So this is Hadoop's both the distributed file system and a processing platform. So the name node and the directory services for the file system are running on these nodes. One of these boxes is set up to interface to the outside world. So that's the basic physical layout of the racks. There's a monitor in here. Every rack has network switches at the top. The machines in each rack are going to connect up to those network switches. There are no cables here because we didn't have the picture when I was getting the presentation ready. I think we have one now. But these machines all connect up to what we call a top-of-rack switch, and there's a pair of switches at the top of every one of those racks. And then the 4 racks in turn, the switches at the top of those racks connect to 2 more switches here, and they are what we call the aggregation switch or the cluster switch. So the 4 racks go up in a tree to the top. And then these units here, it's not really visible, but these are management switches. They're there to do SSH into the machines and remote access so that somebody can manage it. The switches at the top are the data network. So that's kind of the crash course in the physical layout of this cluster. In terms of what's in here in practice, behind the scenes, this is a crash course in the specs. I don't want you to get the impression that I'm trying to promote huge numbers here, but I just wanted to put it into perspective. The servers we used are Dell R720s, which are what we call 2 rack units high. If I went back to this slide here, these racks are 42 units high. Those servers are 2 units. The switches are 1 unit each. If you haven't been in the machine room, this is just the lingo we use. So within here, we use the R720, which is 2 rack units. Each of those machines has dual Intel Xeons. So they're Xeon E5 2620s, which in kind of normal language translates into they're all Intel Ivy Bridge processors. They have 10 cores in each processor. They have 25 megs of cache, and clock rates on these are about 2.5 gigahertz. Every one of those machines is set up with 384 gigs of memory, which is at the high end of what you will see in a Hadoop cluster. That's because this particular machine was designed for Spark and Impala, which tend to use memory very efficiently. Hadoop itself wants to do a lot of disk I/O. The machines in there are running DDR3 1866 megatransactions per second. Storage in each one of those nodes is 48 terabytes. It's set up with 12 4-terabyte disks. Every machine has two 10 gigabit Ethernet interfaces that go into the network, and we actually bond those two interfaces to give us a kind of a logical link that's just shy of 20 gigabits. And then there's a management network. In terms of scaling on the cluster, you can go between 4 data nodes up to 12, 20, and 44 as kind of a sliding scale depending on, and you can also buy just 4 data nodes and add them over time. In terms of total memory, you're starting at 1,500 gigabytes, and you're going all the way up to just shy of 30 gigabytes of memory. So this is a large memory footprint cluster. In terms of storage, you're looking at anything between 176 terabytes up to 2 petabytes. That is raw storage, so I haven't done any fudging on those numbers to account for operating system or Hadoop replication. In practice, you're going to have about a third of that in terms of usable storage for Hadoop, because it's going to make 3 copies of the data. Cores, you're starting with 80 cores. You're going up to 880 at the high end for the cluster. So you've got a reasonable amount of CPU processing. Every one of those cores is running at 2 gigahertz, and it fits in between 1 and 4 racks. And as I said, the reason I'm giving you these specs is I want to now jump in a little bit, look behind the scenes at what drove some of these decisions and help you understand some of the trade-offs here. I can't quote prices on a video, but how much power? That particular cluster needs about 30 amps at 208 volts for every rack. It's very, very dense configuration. Talk to me about pricing later. I'm not going to get in trouble quoting pricing on a video because it'll go viral, trust me. Also, I'm not a sales guy. First, I'm going to jump ahead. Again, let's talk about servers for the moment because that's one of the first decisions. In terms of servers, there are a lot of choices. In the industry, generally we're looking at 3 types of servers. The top right-hand corner there is a 4-socket server. It takes up 4 user rack space more commonly, and it has 4 Xeon processors in it. That type of machine is real popular for big databases, things like Oracle, things like large Microsoft Exchange servers. I think its most important feature, other than 4 sockets, is you can get those boxes with big memory footprints, like 6 terabytes is reasonable main memory. It's a single box. Most of your applications will run on it without any fancy parallelization other than basic threading. The downside is those boxes tend to be kind of expensive. The 4-socket architecture has this little premium on it because you have 4 CPUs and a big memory footprint. Over on the left is something called a blade chassis. All vendors have equivalents to these. These are the Dell model numbers. This is the M1000E. It's a fairly large chassis, so it's 10U, and it has slots that you can plug in all these different modules. So you can plug in processors, memory, storage, and kind of juggle them around. And there's a lot of common logic on the back plane that connects these units together. These are great for flexibility. For companies that are doing virtualization and have different types of applications, they love these blades. You pay a premium for that flexibility. The 2-socket servers are the ones that are incredibly popular with what we call scale-out vendors or scale-out computing. So a lot of the cloud companies, whether it's, if you look at, I'm not quoting Dell customers, but if you look at a Google, a Yahoo, a Microsoft running Bing, and anybody that runs a large scale-out computing organization, they use lots of the same type of machine, and they tend to replicate their configuration over and over again. So these 2-socket machines take up 2U, and we have a class of those machines that actually has local storage. So the pictures here are two different variations of a Dell R730. This one has 12 3.5-inch drives that are hot swappable right in the front of the chassis. This has 24 2.5-inch spindles. The two socket servers are the ones that are almost universally used for Hadoop and Spark. They're pretty good value. They have a lot of storage in each machine. The blade servers, you can put some storage in them, but they're usually attached to network attached storage. The 4-socket servers, you can see you got a bunch of 2.5-inch drives there. I'm not counting them, but I think there's about as many 2.5-inch drives as that 4-socket as there is in the 720 below. They're normally plugged into a network attached storage or a direct attached storage array. With Hadoop and Spark, people love to have their local storage on every single node. So those are the common machines. The next page here is just a whole bunch of text that more or less covers what I just said. I do a lot of presentations like this. So, 4-socket blade servers, 2-socket scale out. The 2-socket stuff is what we're almost always looking at in terms of Hadoop and Spark. Drill down a little. Now I'm going to get geeky, guys. When we look at the dual socket stuff, the basic architecture of the Intel dual socket processors, you have 2 processors. Each processor has 4 connections to memory. You can put 3 memory chips in each, I guess you'd call it a bank for want of a better description. And there's this high-speed interconnect between the processors called the QPI, the Quick Path Interconnect. The latest generation of Intel stuff is known as the Grantley architecture. That's describing the socket organization. And the code name for the processors themselves are Haswell. Top line specs, we can get 18 cores in each one of those processors today. They have 4 channels of DDR4, which lets you go up to 2133 megatransactions per second. They're fast. Some specs on the QPI. The basic idea is you have 2 sockets, memory on each socket, you have an interconnect between the processors. The memory isn't really flat. It's a little tricky. Memory that's local to a processor can be accessed quicker than the memory that's on the other processor. So technically your memory is divided into 2 pieces, these banks and those banks. The Quick Path Interconnect lets a processor make a reference to the memory on the other chip, and it also is used a lot to handle cache synchronization between those processors. This is what Intel called NUMA. It's a generic term, but non-uniform memory architecture. In most BIOS settings, you'll see a tweak where you can set up memory so you have the same access speed to both of those banks, or you can take advantage of the faster speed. My next slide here has a whole bunch of specs on the processor generations. I'm putting it up here basically to show that 3 different generations of processors from 2012 to 2013 to 2014, the latest being the Haswell. These numbers have been going up a little, but you'll notice clock rates went from just over 3 gigahertz to 3.7. They've gone up a little. Process has shrunk in technology. The QPIs have scaled up in speed, but most significantly, we're getting more cores. We went from 8 cores in the Sandy Bridge class of chips up to 18 available in the Haswell class chips today. That's nice to get all those cores. Most of these other numbers are just keeping pace. So we're not hitting a lot of clock rate increases. It's just there are more cores, the caches are getting bigger, but things are scaling out this way. We're not getting faster. It's too expensive to go quicker. In terms of choosing processors, the guiding rule these days is you look at between 1 and 1.5 Hadoop tasks per core, and per physical core. So assume you have like 1 thread running on 1 core. The 1 to 1.5 gives you some headroom for other processes because we normally enable Intel's hyperthreading, which lets us get kind of a parallel thing, where we can use the execution units for multiple threads and the hardware schedules. Hyperthreading works for most jobs under Hadoop and Spark. If you're dealing with highly optimized code, it usually doesn't make a difference. Because if your code was written to take advantage of the processor architect, like some of the lower level NumPy stuff, hyperthreading probably won't help you a lot. The general rule in Hadoop configurations, and I'm talking about processors here, but we tie back to disks, Hadoop really wants to see 1 core and 1 spindle. because most of the Hadoop workloads are a Hadoop job, reading a file from disk, doing something to it, and writing the results out again. So if you have a nice one core, one disk balance, it kind of optimizes your throughput. You can throw more spindles in there. Hadoop really won't use them or take advantage of them. If you're running Impala, which is Cloudera's SQL query on top of Hadoop, it's fast. It's written in C++. It flies. It can handle a lot more spindles and cores. So machines designed or optimized to lean towards Impala tend to have more memory, more spindles, more cores. For Spark, it depends on what you're running for the backend storage. Spark itself likes the one thread or one partition per CPU model. On the disk side, it's mostly memory intensive, so it's not hitting the spindles a lot when it's running, and the storage setup depends on whether you're using HDFS or some other storage array at the back. In general, this may seem counterintuitive, but in general, when you're dealing with Hadoop and Spark, a faster processor with less cores is actually better than more cores. If you throw these 18-core processors in the box, I can only put 16 spindles in there today. So I have two 18-core processors, 16 spindles. I have way more processor than I need. We're actually putting less cores and cranking the clock rate on the processors a little more. That's a common trend you'll see in the processor design. Other than that, you kind of have to benchmark. It's really hard to give you any good guidelines, but most people are following these guidelines. Memory, DDR3 versus DDR4. That's pretty much the decision these days. The newer generation machines are using DDR4. You can get memory in terms of 8, 16, 32, 64 gigs. 128 gigs is on the market now, but it's silly expensive. The sweet spot for pricing is somewhere between 16 and 32 at the server market. It actually depends on current spot prices in the DRAM market. A key thing for performance is we normally balance the memory channel. So if I go back to that processor layout, I had 4 channels to memory. I want 4 DIMMs for every processor. So I'm better off with 4 16 gig DIMMs than I am with 2 32s. If I have 2 32s, it'll work, but I'm only using 2 memory channels. The sad thing about this is your temptation is to put in 2 32s and then upgrade later. Unfortunately, it doesn't work that way. So we'll often put in 4 16s, and then if I want to add more memory later, I'll put in 4 more 16s. Just one of those gotchas in the hardware. This stuff's all server class memory, so it's normally ECC checked. It's usually registered. There are tweaks at the BIOS level in Dell servers to handle some of the optimization of the memory handling behind the scenes. For disk choices behind the scenes, your main choices are 3.5-inch drives, 2.5-inch drives, or SATA solid-state disks. The 3.5-inch drives, they're up to 6 terabytes now. So in the machine I showed you the picture of earlier, I can actually put in the current generation R730, I can put in 16 6-terabyte spindles. If somebody really wants storage density, you can do that. The mainstream stuff is somewhere between 3 and 4. I think the 3 terabytes are the optimal pricing, but the 4 terabytes are moving fast. That's what everybody's using on new servers. 6 terabytes is pushing it for Hadoop. It goes back to that fault zone. If I put 12 6-terabyte drives in a machine, that's 72 terabytes. If my machine fails, that's a lot of data that has to get replicated in the cluster, and it can have a huge production impact. So again, the trend had been bigger, bigger, bigger nodes. Things are now leveling off, and people are going back to wider clusters with smaller nodes because the technology has been moving so quick. For connections, SATA or SAS, doesn't really matter. The SAS stuff is slightly faster. It does a better job of handling multiple requests to the disk because it can reorder them. But in general, Hadoop is doing large sequential I/O transfers. So it's mostly saving data, reading data. It's not random access. 6 gigabyte per second drives are just the standard interface right now. But 3 is more than enough. The spinning platters actually can't transfer data fast enough to handle the SATA 6.0 stuff. SSDs can. 2.5-inch drives, you can get more spindles in a machine, but the drives aren't as big. So you'll see 800 gig and 1.2 terabyte 2.5-inch drives today. I tend to use those for configurations where I know I'm going to be running Impala or doing a lot of interactive query on data. If it's just pure batch processing, there's not a lot of bang for the buck of the 2.5-inch drives because they cost a little more. The SATA stuff, it's expensive. I'll tell you right now, it's really fast, but nobody's going to build an entire cluster, Hadoop cluster out of SATA SSD drives. I just realized, SATA SSDs, I meant to say SSDs there. The SSDs are fast, but they cost more, and the price performance just isn't there. It's like, it works out as something like 10 times the performance for 100 times the price. It's just not worth it. We do use them right now for operating systems and stuff that's scratch space. They do have strategic uses in a couple of places in the machine, but not for the mainstream storage. They're also not as deterministic. SSDs have this garbage collection thing where they reallocate sectors every so often, and you can get weird latencies at times. I'm doing a lot of work in that area to see if that's changing, but at least right now I'm not using SSDs for Hadoop. Quick touch here. I think I'm running tight on time. Am I? How are we doing? We've got a couple of minutes. Trade-offs here. I'm trying to cover a lot of things at once, but a lot of what we're juggling is the spindle, core, storage, depth optimization. The slide has all the details here. Here's what it looks like in practice. If I were to take a cluster, and I'm comparing, this is a model called the C8000, which lets us do very deep storage. I'm comparing a setup that's using 12 spindle disks with 3 terabyte drives versus 6 spindles and 3 terabytes. So I've put more spindles in each machine. And I'm looking at the scaling across my cluster. So I have 3 scales here. The gray line is the number of cores in the cluster. So as I go to more nodes in my cluster using 16-core Xeons, my core scales pretty linearly. But the values here for storage in IOPS 1 versus storage in IOPS 2 are comparing the 6 versus 12 spindles. And by making that decision, how many spindles I'm putting in the machine and how big the drives are, I'm setting essentially the slope of the growth curve for the storage in the machines. So what happens with these 2 red lines here is, as I scale out the cluster, it's always a linear scaling, but I'm controlling how much storage I add as I add nodes. This is an important decision because a lot of people work to their total data size and then go back and say, here's how we're going to scale it. But you have to remember that as you're scaling, you're not just adding storage, you're adding storage and compute. So things go up. The same thing for I/O operations per second. They also scale. And again, you're controlling to a certain extent the scaling rate by making that early decision. We have customers that have gone out, rolled out a cluster and only put like 6 drives in the machine, and their plan for expansion is they're going to go back and put another 6 drives into the machine later. That's not a bad strategy. The one gotcha with that is, apart from having to physically touch the machines after installed, which gets expensive just because you got to send a person in. But the trick to that strategy is when you go back and touch all those machines and add extra disk, you still have to do a rebalancing in Hadoop. But I've seen people do that, particularly because if you put, which is common these days, 12 3 terabyte spindles, 36 terabytes of data per disk. If it's a small cluster, if you've got a 10-node cluster, 10% of your data is on every one of those machines. After replication, it's more like a third. So if you lose a machine, you're not out of luck. The data is replicated, but the cluster fault zone gets big. So I'm seeing people use smaller data nodes unless they know the cluster is very big. So that's the scaling. Networking. I do need to touch on this. I talked about it on the beginning picture. It's basically a tree. There's nothing fancy going on here. We take the nodes, we bring them up to the top of a rack, and we use top of rack switches, and every node has a connection to the switch at the top of the rack. Every switch at the top of the rack has a connection to an aggregate switch at the top. That's the basic model. It's a tree. This works for clusters getting into hundreds of nodes. If you want to build a 1,000-node cluster, those top switches get saturated, and there's some other tricks we use, but this is going to work for a fairly large cluster. What I do with most of my architectures is I run 2 10-gig links to the top of rack to 2 alternate switches. And I use a feature called VLT, which is a form of stacking. We can connect those 2 switches so that they act as one logical switch. But if one of the switches fails, the other one can carry the load. So I build a certain amount of redundancy for a switch failure in the cluster. Going up to the aggregation switches, the uplinks are 40 gigs each, and each one of those switches has 2 links to 2 alternate aggregate switches. So I have from each rack, I have 4 40 gigabit network connections going up to the cluster aggregation switch, which covers me if I have a switch failure, I lose half my bandwidth, but my cluster doesn't go down. If a cable fails, I lose some of my bandwidth. And I've got the bandwidth. If everything's working, I can use that bandwidth. So that's the basic model. The next slide here has, I think it says what I just said. Couple of points. This stuff is all layer 2 switching. So there's no fancy, tricky routing. Frankly, our home firewall does more packet inspection on packets than we do in Hadoop because we want it to go fast. So switch characteristics, a lot of line rate switching, no latency there. Deep buffers because you can have a whole bunch of machines connecting to one. VLT is that stacking thing that lets us pair up switches. We do 40 gig uplinks. 10 gigabit Ethernet is the norm for clusters. Gigabit you can do today. 40 gigabit for all the machines is too expensive and the software doesn't use it. In the wild, just to give you a perspective, I talked about that appliance configuration, but in terms of what our customers run, the vast majority of them are running that R720XT. It was the previous generation 2U socket server. We have a bunch of customers running that. Dual socket, they typically run 12 cores. I got 5 left? Oh, wow. I'm on ahead of time. Mostly 12 cores and an awful lot of people running the 24 2.5-inch drives. There's another model, C8000. It's popular for really what I would call deep applications. With Hadoop, Hadoop is for people that use their data. You'll hear us saying that it's the cheapest storage system out there, and I don't agree. There's cheaper ways to store data reliably, but if you want to process the data, you can't beat Hadoop. Because every time you add storage, add processing. The C8000 with 16 3.5-inch drives, 4 terabytes each, is pretty popular. I can actually do a variation of that with over 20 drives on it. It's really deep storage. It's used a lot for archival. There are some people that are bringing in logs or machine logs or just generally transaction history, and it's archival. They got regulatory reasons that they have to keep it around for 3 and 5 years, but they really only process it once. They do one pass through the data, they roll it up or extract some fields they're interested in. The rest of it's just archival. You can do deep storage. There are some older models we've used. A lot of our bigger customers have repurposed machines, the 6100s and the 2100s. These were originally built for web serving. So some customers have taken those machines, repurposed them to Hadoop clusters, and replaced their front-end web application machines with newer models. So you'll see a lot of this sort of thing happening. You know, machines that come on the market that are the last generation, they actually either come on the used market or within a company, they just repurpose them. There's another machine we had built for cloud computing. It gets used quite a bit for Hadoop, but it's actually a really bad balanced machine. We've had customers use this, but this core spindle rate just doesn't have enough spindles. You can put 16 cores and only handle 6 drives. Not a great setup for Hadoop. R620s are popular in 1U. There is a religious war in the Hadoop world over should you use 1U versus 2U servers for Hadoop. A lot of people are actually going in the trend of a smaller server and more servers. In terms of pricing, the 1U servers, when you put enough storage in them, they start working out to be more expensive than the 2U servers that can have a lot of disk space in that single node. So people are using 1U, but I wouldn't say it dominates the market. So I've had a crash course in hardware. So I need to wrap up. In terms of Q&A, I mean, we could start Q&A now, but there's things I haven't touched here. I haven't touched GPUs. Grab me later. If you want to talk about GPUs, it can be done. Not many people are doing it. If you're doing tons of data streaming, you know, there are special configurations we want to use. And I think one of my pet projects is to look at a machine called the Dell Vertex. It's kind of a side project. It's kind of a blade chassis that was built for small and remote offices. And it's got a bunch of processors and a bunch of disks. So it's kind of nice as a killer data science workstation. It's like a production grade server that you could fit in a normal office environment. So I'm going to play with that, but I haven't talked about it today. So thank you for attending, and any questions here as we're wrapping up?
Do you have any comments about like the PCIe SSDs, like Fusion Atom type?
Yeah, it's a good point. So in a half hour, it's hard to fit everything in, but we have a set of machines that do support PCIe SSDs. So these are a flash storage device that literally sits on the PCI bus. They are fast. For Hadoop itself, they don't make a lot of sense right now because Hadoop has this brute force approach that it assumes reading and writing disks. Always, that's the binds. Spark, on the other hand, is evolving with the file system called Tachyon to have a hierarchical storage. I think those PCIe SSDs are going to come into play there. Because you have a memory hierarchy. You have cache, main memory, persistent storage is just flash, and spindles in the back end, and you have software that can manage that hierarchy. Really interesting stuff there. But today for Hadoop, they don't pay. I'm stealing somebody else's time, so I'm going to wrap up here. And if you want to ask questions, just come up and grab me. I can talk about this stuff all day long.